Good afternoon, everybody. Thanks so much for coming. I'd like to acknowledge that we are gathered today on the traditional territory of the Gitumden clan of the Wet'suwet'en Nation. My name is Dawn Hansen. I am Operations Manager at the Bulkley Valley Research Center, and it's my great pleasure to facilitate these seminars. This is our last seminar of the season. It's been a great year, and really appreciate all of our presenters and all of you for your interest and attending. I would like to acknowledge Wet'suwet'en Community Forest for their funding support for us to purchase this technology, along with Bulkley Valley Community Foundation and Bulkley Valley Credit Union. It's allowed us to have the cameras and the good sound system and be able to present in dual world. I would just like to give a warm welcome to Don Morgan and Andrew Fall, and looking forward to their presentation today on TEF. I'm going to leave it at that. I'll let them explain what all the excitement is.
Some of you know Andrew and I. We've been working together, 20, 25 years, and involved in a number of projects. A lot of land use planning, North Coast Land and Resource Management Plan, the lakes, the Maurice, Iskitskeen, Haida Gwaii. Andrew's done a lot of work with the mountain pine beetle. That was I used to be with Ministry of Forest Research Branch, and we took on the mountain pine beetle file and then the modeling for the mountain pine beetle, how that would play out. So that was kind of using this similar modeling system that we that Andrew's built the this wildfire model in called CELES. Anything you want to add to that, Andrew, on the background of kind of the modeling?
Not really. I guess the only thing I'd add is I've been doing things around Maurice and Bulkley area for a long time. I did analytical support for the Maurice LRMP, Land and Resource Management Plan, way back, and I'm currently involved with the support for the TSR and the FLP project.
Great. So I'm going to show a couple of slides to begin with, just on the Bulkley-Morice Wildfire Resilience Project, some high-level slides, and then we'll go into some context and then the framework that we've built out for this for modeling wildfire in this area, and then Andrew's going to dig into some details about the various components. Next slide. Oh yeah. So we all kind of know what's going on with climate change. There's forest conditions have changed over time, fire exclusion over the last century, kind of leading to this, seemingly increasing risk around wildfire. We're starting to see wildfire a lot more, but really kind of the backdrop is kind of happening all over. Next slide. And there's more information on this on the side panel here. We have some posters here, and if you want to pull any of Jeff or myself aside afterwards, if you want to talk a bit more about the kind of project and logistics. But essentially, we've got these kind of two main goals around improved stewardship and safer communities. When you're doing these sorts of projects, you want to sort of establish some aspirational goals that you want to kind of work towards. We're really involved in kind of phase one right now, which kind of runs until March of 2027. And we'll be talking about some of these pieces. The knowledge report that's pretty close to being out there in the public realm within weeks, and it's been formative for kind of having a solid scientific basis for the work that we're doing. And then phase two, we've got funding going forward, so and we're doing some work planning on what that's going to look like, and a lot of that's going to kind of emerge from the work that we're doing right now. We plan on having a workshop at the end of November, a larger workshop at the end of November, probably at the Hudson's Bay Lodge, bring people in, again, do some presentations. And really, we've kind of done this all along. We had a big workshop last December, and kind of getting folks in the room, presenting products that we're developing and knowledge that we're finding, and having good, thorough conversations with practitioners and community. Next slide. So the funding is coming from the Gordon and Betty Moore Foundation, and the project's administered through the Valley Research Center. We have a steering committee which is made up of local First Nations, Wet'suwet'en, Lake Babine Nation, Chislata, Gitxsan Chiefs, the BC Ministry of Forests, BC Wildlife Services. I'll say wildlife every now and then because that's actually my background is on conservation planning. And then we have some forest sector representatives. Matt Sears from West Fraser has been joining us lately, which has been great. Next slide. Study area. So we're really kind of focused on this kind of Bulkley-Morice timber supply areas and the overlapping First Nations. So that kind of defines our boundary. And then analytically, we put a 50-kilometer buffer around it because fires burn in and fires burn out so that we can keep track of all those events. And some of you know this story. There was quite a bit more frequency of fire back at the early part of the 19 kind of, well, the fire record, really the one that's digital, starts in 1919. Kind of going back further than that, you have to sort of reference old handbooks from various rangers that were out on the land and wrote down what they saw in the landscape. But unless you do some reconstruction. But then there was this kind of lull in kind of from the, really from the late the 40s, early 40s to the 2000s. And then it's picked up again since the 2000s. And a lot of that's kind of related to, I mean, we've had other seminars kind of talk about this. Phil Burton's been working on, and a group of us have been working on redefining the fire regimes in the area. And so we see these kind of long-term oscillations due to ocean atmospheric patterns, Pacific Decadal Oscillation, El Nino, and so forth. Next slide. This next one just shows the fire size. And so we're seeing larger fires now, which you could hypothesize is a result of kind of land use practices over the last 100 years, the exclusion of First Nations burning on the landscape, for example. So we're working through this kind of this risk model where we're looking at hazard and vulnerability. So this is a common model. So hazard defined as likelihood and intensity, and then vulnerability, exposure, and susceptibility. So the modeling we're doing right now is really focused on the hazard side. We've got some posters there. We'll be diving into this about how we're modeling likelihood and intensity. So really it's getting at this, is there a benefit from strategically placing treatments? So can you get to 1 + 1 = 3? So that's kind of just at a high level. We want to kind of look into that question, and at what scale do you get this effect? And is there at some level that you no longer get that benefit just because you're of landscape ecology? You get to a certain place, if you're treating everywhere, well, you're not getting any spatial benefit from where you put it anywhere because you've treated all the high hazard sites, for example. But we'll get into that a bit more in the details. Next slide. So this idea around stand scale treatment effectiveness, again, we just kind of came up with this graphic to kind of show, what's the bump, what does this look like? So we're going to try to generate a curve like this with the modeling data and what we're seeing through these scenarios. So why model wildfires? There's a number of reasons, and there's the model that the team has kind of developed is really focused on this kind of hazard component and looking at communities and values in the landscape. Other models are better for suppression, might be better for strategic planning, for timber supply assessment. They might be more value specific, but the model we're focusing on here is really focused on the hazard question. Next slide. So this is just a really high overview of what TEF does. So it simulates wildfire ignition, spread, and extinguishment. So those are the big pieces of it. And then we can explore these landscape level treatments and land scale, and then kind of look at what the options are around fuel breaks, what those fuel breaks might look like, where they are, how they correlate with other values in the landscape, ungulate winter range, high timber values, important cultural sites. And the other thing to bear in mind is we with these kind of models, we don't predict the future. What we do is we run it thousands and thousands of times and then look at where fire might occur more often than other places. So you're going to see drier places with lots of fuel are going to burn more often than places that are wetter with little fuel. So you'll see some of those results here in the deck. So this is not a predictive model. It tells you where fire is going to be. It simply tells you where it's more likely to be. And it's relative and not absolute. So when we do comparisons, we're comparing A to B, but neither one is an absolute thing. It's just that we know there's a difference if you do this or if you do that we see a difference. So we're trying to provide guidance to processes like the forest landscape planning that's going on in the Bulkley-Morice, to timber supply analysis that's happening, to wildfire management planning. So we're just providing guidance into those processes and say, hey, look, these are kind of what we see in terms of how these pieces fit together. So we just wanted to kind of outlay some of these modeling principles so folks are familiar with our thinking. So we've got this, as I mentioned earlier, this knowledge report, and really we're trying to draw as much as we can from empirical information in order to build these things, and have a rationale as to why we have certain assumptions built into the model. We want to always trace back to the literature, and so we use the knowledge report as our foundational piece of information to kind of rationalize what we're doing. We're transparent. We're using all open source software. The R code, for example, is all up on GitHub. People can go and pull that code down, look at it. CELI's, the TEF code, the time-based empirical model, is available on request right now. At some point, we'll probably end up putting that again in a GitHub repository as well for download. So the principle, though, is that this is all open source. The idea being that it's repeatable. So it's publicly available data for the most part. There's some data, that is not necessarily publicly available, although you could do variations that are publicly available. I'm just thinking in terms of some of the burn severity type information. But we are in the process of developing with Eclipse GIS, Johanna's here, a portal to access results from the information on some of our input layers, and also having a mapping, using the Skeena mapping portal to look at data, so people that are curious, but also being able to pull down these detailed rasters from the repository. And then collaborative, we're working with a number of organizations, with BC Forest Analysis and Inventory, that's the timber supply folks, we're working with them. Forest Ecosystems and Analytics Branch, we're working with Colin Mahoney's group he's the chief climatologist for the province. You'll see some pieces that'll come up here where we're using some wind modeling that they've developed in order to understand how wind behaves in the landscape and then drives fire. So these are some of the core outputs. And as I said, there's some posters on the wall too that you can look at after the session as well in more detail. But this idea around likelihood and intensity making up what is hazard. So likelihood, there's 10,000, you burn 10,000 fires, and they're all starting randomly. Andrew will get in a bit more detail about how that works. And this is showing areas where, in the darker colors, where there's more likely fires. And then intensity is a function of the heat, fuel consumed, and the rate of spread. And we're kind of backstopping this using the Canadian Forest Service's fire behavior prediction system in order to kind of come up with the equations and so forth. And you'll see more than that than you'll probably like later. Next slide. And we have these supplemental pieces around rate of spread, crown, surface, and fraction burned. So we're trying to really stratify, what's a crown fire, what's the surface fire, ladder, trying to get at these different dimensions of wildfire. And then fire pathways. So looking at some area of interest, this one here is the wildland urban interface in the Bulkley Valley, and the strings you see are kind of the pathways that connect to that interface. So where are the fires coming from that are hitting that interface? So you can see a lot of them. The less in the north as you get into the wetter kind of ICH type area, and then in the drier areas you're seeing more where there's a higher probability of fire in those places. So just to kind of summarize the overall framework, we've got this likelihood, areas that are more or less likely to burn, fire intensity, so that kind of tells us a little bit about management and the impacts, crown and surface fraction burned, informing kind of what you do in a stand, for example, fire pathways, and then the rate of spread, how fire could move, how fast it could move. So those are kind of the pieces we're going to now dive into in the modeling, about how we model these pieces. Okay, I'm going to hand it over to Andrew now. and he's going to provide a bit more detail on these pieces. But you've got the kind of picture of the framework, and now we're going to flesh it out.
Okay, so hopefully my audio is okay. So the what I'm going to do is try to describe at a fairly high level and fairly quick level the structure of TEF, what's involved, what is it actually doing, and it'll be fast because I think we want to get to results and being able to look at what the current results are. So the general idea behind TEF is that each model fire, so we're going to run lots of fires, but each model fire has to ignite somewhere on the landscape, spread across the landscape, and extinguish. And repeated simulations are used to identify which areas of the landscape are more likely to burn frequently and which ones are not likely to burn frequently, either because of where they ignite or the relationship of their position on the landscape. The rate of spread, so when the model is spreading fires, it depends on the fuels that it encounters, topography, primarily slope and aspect, and daily weather attributes, including wind speed and direction, so fires burn with wind, buildup index, and fine fuel moisture code, which relate to prior weather, fire weather, temperature and heat that's been building up in the system over time. Grass curing, which relates to the state of grass when grass fuel types are encountered. This is all based on the Canadian Forest Fire Behavior Prediction System, the FBP system, which I'll talk a little bit more about. What TEF does is it integrates these elements together, weather, fuel patterns, and topography over a large landscape. The study area is millions of hectares and includes both the Bulkley and Morice timber supply areas, plus some portions outside to the north and the south and east. It's meant to be flexible to be able to assess a range of different scenarios. It's reasonably fast, and why I put reasonable in quotes. It takes about 30 to 40 seconds per modeled fire, which is pretty good if you think about all the calculations that need to be done, but it still takes many days to run a scenario. If you're running 10,000 fires, you can do the math and you're waiting for the computer to run. So we'll go through these pieces one at a time, focusing mostly on spread. Fire ignition. In the TEF model, fire ignition doesn't represent where a fire necessarily just starts. It's not about where the lightning hits. It's when lightning starts a fire that's big enough to burn at least 1 hectare. So it's a fire, what we call a fire escape. So the fire has to start in that cell. And it can be a source of, it come from lightning fires or from human fires. That is, the ignition locations are selected using an input layer, a relative probability surface of where lightning fires and human fires are more likely or less likely to start. The other aspect of ignition is that we're using historic weather to drive the sequences of wind and build-up index and so on over time. So we have 11 years worth of data, 2014 to 2024. When a fire starts, it picks a location, and it also picks a year and day in the year for when that fire starts. And that is picked on a distribution of when historic fires did start in a season. So you get more fires starting in July and August than you do in April. The lightning caused fires are based on the Provincial Strategic Threat Analysis, provincial data on lightning fire density. And the left image shows that information for the study area. Now we know that fires start in the, they start, this is actually, the number of fires used to generate that data are relatively small to produce a whole surface over millions of hectares. Not everywhere is burned since this data has been collected. So we accumulate, or we assess that lightning fire density data from the province by the historic natural fire regime, which is a classification developed by Laurie Daniels and others at UBC, and natural disturbance type, which is related to the biogeoclimatic ecosystem classification. So we join those two data types together, summarize it up, and get what we call a relative ignition likelihood. In that image on the right, the purple areas are basically neutral. They're kind of where fires are relatively random compared to other areas in the landscape. The areas that are blue and light blue are areas that have less likely to have fires. So in the mountains and on the coast and in the north, fire frequency is about half as frequent as in areas that are in the plateau. And the areas in yellow are higher likelihood. Those are areas where the fire record has shown a higher frequency of fire ignitions than in other areas. You can do something similar for human-caused fires. On the left, that's also from the province, human fire density, where the ignitions are from human fires. Here, what we did is we overlaid the wildland urban interface on top of it, and that's the darker areas on the right-hand side. It's otherwise the same. What you can actually see is there's a very high correlation with where people are, where structures are, where habitations are, as well as where roads are. So that's what is the highways, major roads, and the wildland urban interface are used to condition that probability surface. Today we're not going to talk a lot about human-caused fires. The results to date focus on lightning-caused fires. The second element, actually it's the third element, but I'll cover it because it's a lot easier, is extinguishment. The large fires tend to go out when a fire-stopping event occurs, and we're not modeling those fire-stopping events. What we do is we pick from a distribution based on historic fires how long fires tend to burn. So we know that fires tend to burn on average, and if we look at the last few years, the average is around 20-something days, 27 days, plus or minus. They can be as short as a couple days. They can be as long as 40-something days. So that's a distribution. Every fire that starts is a duration. The number of days it's going to grow for are selected. And when that time is reached, TEF simply assumes that a fire stopping weather has occurred. So it's quite simple. That's the structure of the model. We're not trying to predict when fires go out. We're just trying to replicate the distribution of how long fires burn in the historic record. Fires may also go out in individual stands because the rate of spread stops to reaches zero or hits a non-fuel type. So there's individual extinguishments, but the primary reason a fire goes out in the model is because it runs out of time. The main element of the fire model of TEF is rate of spread. And so that's the core aspect of it, and I'll spend a bit of time on that. Rate of spread can be driven in TEF by either the fire behavior prediction fuel types, and I'll come back to that, or by statistical data, by empirical data collected in the field on fuel types. We have a version of data or a set of data that we're looking at with Dr. Phil Burton in Lakes area to look at that. But for the rest of this talk, we'll be focusing on the FPB fuel types, which are on the right-hand side. Spread is also driven by topography. Wind drives weather. Wind blows fires forward. Slope and aspect, we know that fires burn uphill. Fine fuel moisture code and buildup index relate to prior weather conditions. So fire weather, that influences how fast fires can spread. So we'll cover a little bit of those as we go. For those not familiar with the CFS fuel types, there's 16 fuel types that broadly group the landscape into coniferous, deciduous, mixed wood forest, slash, which are where there's been some post-harvesting, post-logging, and open grass areas. This is what they look like in this area generally, their categorization. So the C2 boreal spruce is got branches, a bit more open, branches that go down quite low. So there's ladder fuels. Mature lodgepole pine, more open, higher branches, so different burn characteristics. Red and white pine, which is more of an Ontario species, but that's a fuel type. Ponderosa pine that we don't really have in this area. Douglas fir. And the more open types, post-logging, pine slash, maybe more recently after logging, fir slash, different characteristics, different assumed remaining fuel. Immature pines, these are more plantation types and post, regeneration after fires. So there's all these fuel types, and every year the province produces a layer of the fuel types. Now you'll see there's a few more than the 16 types. The province also classifies areas that have recent burns. So if you look in the south of the study area here, there's a number of recent fires in the last decade, and those are prefixed with a B, a burn, and related to the severity of the fire. So there's these fuel types. Now, the reason for using those fuel types, so on one hand, we know that those fuel types represent a oversimplification of the fuels that are represented across the landscape. Not all mature spruce stands are equal in terms of fuel. We know that, but the reason we use the fuel types is because there's a well-developed history of empirical testing and development of theories behind how fires spread in those fuel types. And I'll come back to that in a moment, but that's the main reason we're using that. Another reason we're using those is because BC Wildfire Service and other practitioners in BC use those and rely on them for other aspects of fire management planning. Now, rate of spread in TEF is based on these fuel types depends on these elements. And what basically happens is TEF joins them together, where fires tend to burn uphill faster than they burn downhill. They tend to burn faster with the wind than against the wind. They tend to burn faster when the fine fuel and the prior weather buildup are more conducive, more drier conditions, hotter conditions, and they tend to burn faster or slower depending on the fuel type. Those elements combine together to result in the rate of spread in a given 1 hectare grid cell in the landscape. And that is calculated with a lot of equations. I'm not going to try to unravel those, but these equations are one of the main reasons why we use the CFS fuel types. Because those equations exist, they're documented, they've been developed over decades of work by the CFS, validated and tested and updated. So to do something else requires going out and doing a lot more research, and whereas we can rely on these equations and calculate from all those factors the resulting rate of spread. So that's what TEF does. It takes all that information, and at any point in time as a fire expands for any given 1 hectare grid cell that's burning, it'll calculate the rate of spread in all directions to the neighbors with the possibility of spotting. So in the direction of the wind, usually the fires can jump up to 1 kilometer or more away over top of non-flammable fuel types or non-flammable types like a lake or a river. In addition, the CFS system, the FPV system, includes a calculation to estimate fire intensity, kilowatt per meter. So that's a heat measure, or energy released. And that's a function of the rate of spread, and as well as an estimate of the fuel consumed and the heat of the combustion. So those are used to calculate an estimate of fire intensity. Now we've got these two elements, the likelihood of burning and the fire intensity that Don mentioned. So before I get to results, how good is it? How do we know the model is doing something reasonable? Well, the first step, once we get all those equations, is calibration. So there's some adjustments. There's a lot of variables that can be adjusted. A calibration step is done looking at each of the large fires in 2018, all the fires that are over 100 hectares, 34 of them, matching conditions as much as possible, starting the fire in the model in the same location as those fires started, on the same date, running them running the model for the same duration if the fire burned for 10 days or 30 days, using the same daily weather, and coming out with an estimate of how to adjust the rate of spread to match as close as possible those fires, and doing that for all 34 of them. And what you get is not a single factor. What you get is a adjustment, and I'm not going to go into the details. Anyone wanting more details on calibration and validation can talk to me afterwards. But basically, you can look at, to do that, you run TEF on each fire, run it many times, and then develop an estimate of what is the threshold where TEF matches the fire as well as possible. Now, validation, that's calibration. Now we've got the model calibrated and we can run it. The validation is assessing the model using independent data, using data that was not used for calibration. So we did that using 2024 fires, 19 of them. And the first test was to compare the calibration, recalibrate using those fires and compare if we get something similar. And the graph at the bottom, and I won't go through it, it kind of shows that they're pretty good. The calibration of the 2024 fires isn't so far off from the 2018 fires. The real test is actually when you run the TEF starting in the same start date as those 2024 fires, in the same start location, and then running it many times and comparing with a null hypothesis. So when we do this is an example with the Wells fire. The fire started in the southwest corner. The dark areas, the gray outline is the fire itself. That's the perimeter of the fire that resulted in 2024. Then the shading shows 3 independent runs of the model. Those are just 3 examples. Sometimes the model results in a fire that's smaller. Sometimes it results in a fire that's bigger. When you run it many times, you get a likelihood surface. That's, where the yellow and red are high likelihood of burning in a run. The blues are lower. And you compare that with a null hypothesis, which in this case is a circle. If the fire just spread out in a circle of the same size, how good is that? And then you can test that. So we don't, we do this for 34 fires. We don't care about the images. We care about the statistics, and we can compare the agreement of the model fires with the actual fire compared to the agreement of random fires. So how much do we get an improvement in agreement? So I'm not going to go through those too much other than to say the model does reasonably well. You wouldn't expect, because of the high level of variability and uncertainty in modeling wildfire, you don't expect a model to be able to get a perfect match. We're not trying to predict the Wells fire, for example, the Mount Wells fire. We're not trying to predict that exactly. We're trying to say that that's actually a high likelihood that when you run the model many times, the Wells fire actual perimeter is a relatively high likelihood, has a high likelihood of being an outcome of the TEF model, because there are other factors that we aren't including in the system that cause a lot of variability and uncertainty. So if you want more on that, ask afterwards. I think at this point, we'll say we have a model that's been tested and pushed around. It has been calibrated and validated, and it matches reasonably well. And now we can get to our main runs, which I'll cover here. So what the base run with lightning caused fires is assessed by running TEF 10,000 times. The fire starts, each fire is ignited using the process I described, spreads out to a specified duration selected from those distributions. When you run it 10,000 times, then you get an estimate of where on the landscape are fires more likely to experience fires compared to others. So you can see certain patterns. The west in the mountains towards the coast has lower likelihood. That's green. Those are lower values. The blues are medium values, and the reds, purples, and yellows are high values. The average times burned is 21 times, mean fire size of about 20,000 hectares, and a mean duration of about 27 days. What it's showing, if you want to get into, we can afterwards certainly ask questions about what the pattern means, but what it generally means is, or indicates, is that areas that have a lot of areas where the pattern of fuel lines up with the topography, so where the fires can burn uphill through continuous fuels with the direction of the wind. So if you're on a slope rising in increasing elevation in the direction of the wind, or where the wind's pushing it, on the lee side of lakes. When you get on the windward side of lakes, I should say, when you get on the lee side, on the side of the lakes away from winds, like Lake Babine, you can see the effect of large lakes. So when the wind is generally blowing from west to east or southwest to northeast, and the windward side of large lakes has an effect. The pattern of mountains, the pattern of fuels has a large effect. You may also notice that south of Utsa Lake, there's a large green area. That's related to the fuel. The fact that there were these large fires in 2024, the fuel typing in that area indicates that the fuels are, they're not really, there's not enough fuel there to carry a lot of fire right now. Now that's related to the fuel typing that's used as input. One of our tests will be to assess whether or not those types are whether that's reasonable or not, and what would happen if those types are more flammable, if they're more like grass or slash than they are low fuel types. But that's the likelihood of burning. The intensity is the kilowatts per meter. That's the heat. So the patterns are different, and that's the key thing. The areas that are reds and blues and yellows, those are where the fire burns on average with more intensity than other areas. So it's a relative intensity. You should look at these. So you can see the Bulkley Valley, or if you're familiar, if you know where your place is, the Bulkley Valley has lower intensity because there's less fuel. A lot of the fires burn when it's grassy ecosystems that are not cured grass, so not very hot. Where you get high intensity tends to be in the mountains, actually in areas that have more fuel buildup. So a lot of this is correlated with larger spruce stands that have they may not burn very frequently, but if they burn and when they burn hot. And you see, those who are familiar with the Nadina fire and some of these more recent fires may see a mixed inside the fires perimeters. Recent fires, there's a mixture of either low intensity or very high intensity, a bunch of yellow, and that's related to the fuel typing. Fuel typing in recent fires is a challenge. We talked about that in the December workshop. We've adjusted fuels in there in recent burns, but it is a challenge because of the way the FBP system responds to fuels of different types. If it's grass or if it's slash versus shrubs, deciduous, those have very different intensity outcomes. So now we'll combine those together into hazard. The equation is there's different ways to combine these. What we've done is multiplied them and taken the square root. Now, you combine them. So if you have an increase in the likelihood of burning, then, so let me put it this way. If you have a high likelihood of burning and an average fire intensity, or a high fire intensity with an average likelihood of burning, you're going to have fairly high hazard. You have very extreme hazard when they're both high, and you have low when one or both are low. The reason for the square root, and this is for the mathematicians in the audience, is because likelihood of burning and the estimated fire intensity are correlated. They're not independent. Larger fires tend to be more intense. More intense fires tend to be larger. The correlation is not 1-to-1, but they're correlated, and so the square root kind of combines that as a geometric mean. To keep this relative, because we're not trying to focus on absolute values for hazard, we normalize that by scaling it from 0 to 100. So when you look at a layer like this, it's really just to be interpreted as a relative scaling of greens and light blues are relatively lower hazard. The reds and yellows are relatively higher hazard. Fire pathways are also outcome when the model is able to take as input a focal area, in this case the Bulkley Valley Wildland Urban Interface. Whenever a modeled fire hits that or arrives at the perimeter of that wildland urban interface, the model can trace the path it took and accumulate that over the 10,000 fires. So this is the sum, the accumulation of all the fires from where they started, where they ignited, to the point where they hit. The value of this, and I think we got a more closer up one. The value of this is it can help identify the directions and relative hazard or risk or likelihood of fires arriving at areas of interest, in this case, the WUI. So if you look in the Smithers-Telkwa area, you can see a bunch of yellow around, that's actually around Telkwa Valley. That represents a relatively high likelihood that if fire, if the direction of risk to reach that wildland urban interface is from the west, coming out of that valley, not down the face of of Hudson's Bay Mountain, not from the north, but primarily from that west and southwest direction. We can compare different attributes. So Don showed some other metrics that can be looked at. Fire pathways times burn. You can compare that with the rate of spread. Some fires burn very fast, some burn very slow. You can take the average of that and identify where's the fire more likely to be burning quickly, which is a metric that might be useful for looking at where you might want to reduce or where it's more likely to have the potential to suppress. Maybe I'll just leave it there and hand it back to Don to do a few slides.
So we're just going to talk about the scenarios that we ran. And as we were mentioning, it's kind of this idea of treatments placed along, control lines or within a fuel break versus just treating high hazard on the landscape. And as well, what about treating just only the high hazard in these fuel breaks versus treating everything? So these are kind of some of the moving parts, but basically the two big ones are the hazard focus, so you don't care where it is, you're just going to treat all the high hazard stands, versus treating this kind of pod focused. Yeah, so there's been a pod project going on for the year. Pods are potential operational delineations. They're quite commonly used in California, for example, and around identifying where these good control lines are, how you can maybe contain fire where there's maybe some natural features, lakes, rivers, mountains and so forth, that you can kind of imagine. We got a picture of it later on showing some of these draft lines, and we've got a poster on the wall as well. Yeah, here's the picture. I don't know if this is showing up very well, but you can see these white lines. You see things like the mountain ranges, or kind of you draw a pod boundary around that. Obviously there's not much going to burn in there, but then the line work gets a lot more busy around the interface with communities. Because you want to have a lot more control features and you want to have a lot more kind of management happening in there. And the idea over time is to develop, objectives for within each one of these kind of units, as well as what you do on the various lines that make up the unit. Is it a road? And then what are you doing along that road? Or is it a river or a wetland complex? And kind of thinking through about, what you're going to be doing where as this kind of matures. So, Andrew, I'm going to pass this over to you to we've got these, I'll just briefly, these, we were saying, with this base case, the pod treatment, and the high hazard fuel treatments. So this table just kind of outlines what we're looking at for what the model kind of ran. And we're looking at a couple of assumptions I just want to be really clear on. We're assuming that a treatment is 100% effective. So that when you clear 100 meters wide, that fire does not burn in there. And then we looked at 100 meter, 300, and 500 meter kind of these lines, these treatment widths along a line. Andrew?
So these scenarios are not designed to be practical. They're designed to help identify the degree to which treatment may influence or reduce fire hazard and likelihood of burning on the landscape. And that's why we made assumptions like Don just mentioned. So we're going to assume for a first set of scenarios that a treatment is 100% effective. We can test that, there are plans to test variations on that. But for now, just to keep it simple, a treatment is 100% effective. The pod treatments are going to look at those pod lines and either buffer them by 100 meters, so 100 meters wide, 50 meters on each side of the line, 300 meters or 500 meter wide swaths, and treat either just the high hazard fuels, so the fuels that have a relative hazard of above 50%, or all fuels. So those are the two types of pod treatments. And that the amount of area we're talking about for the study area ranges from 13,000 hectares at the low end, 100 meters, just the high hazard fuels, up to 353,000 hectares. So a wide range, and the 13,000 is closer to feasible, 350 obviously unlikely to be feasible, but we're just trying to identify what is the effect on the outcome. For each pod scenario, there's a corresponding high hazard fuel treatment, or HHZ fuel treatment scenario, that is the same as it treats the same area, the same number of hectares as in the pod scenario, but focuses on treating high hazard fuel, the highest hazard fuel anywhere on the landscape. So it's really take your treatment budget and treating it in the highest hazard fuel, as opposed to using it to treat areas in pods. So this is really to test what happens with different pod widths and areas treated, and what happens when you if you're compared to not using the pod lines.
Hey, Andrew, I just want to point out to folks that harvesting capacity is 4,000 hectares a year roughly for the Bulkley-Morice, 2,000 in the Bulkley, just to give you a sense of what kind of capacity there is to create treatment areas if you were to reapply that industrial work to treating the forest. So it might take you 3 years to kind of get to that minimum amount of 13,000. Would take you maybe 3 years of harvesting to get to that place.
So some of the fire research indicates that up to 20 to 40% of a forested landscape needs to be treated to really disrupt wildfire spread. That is not likely to be feasible. That in our study area, that would represent between 700 and over 1 million hectares. So that's just not really on the table. But the effectiveness, what we're trying to test is how effective, does affect in the degree to which you can place those treatments strategically to increase your effectiveness. And so, you can have pod, as has been shown earlier, you can have them focused on pod lines, you can treat high hazard fuels, and there's a lot of other scenarios that may be assessed in the future. So these are a summary of the scenarios, the outcomes. This is the results. I'm just checking my time. I think we're okay. So these are the six pod scenarios, and the first column or the second column, the percent and hectares treated, that's the input. That's how much area is treated. So if we take all those pod lines that were shown on the previous slide and treated all the high hazard fuel in those areas, the high hazard defined from the base run, 100 meter wide pods would result in a treatment of 13,000 hectares, 0.4% of the landscape. So not very much of the landscape, but still a significant amount of area. That results in a 4% reduction in the likelihood of burn over the whole landscape. Now we can also talk about specific areas of the landscape and so on. We'll get to that. But over the whole landscape, treating 13,000 hectares, 0.4% of the landscape, can result in a reduction of 4% of the likelihood of burning. It doesn't reduce the mean intensity as much, and so the reduction in relative fire hazard is about 2%. The next size up, what if we made the pods wider, 300 meters? That'll disrupt more fires. They have a harder time jumping over it. Only faster fires would be able to breach that distance. If we treat only high hazard fuel, of course, that's not fully breaking the pod lines. That would be 0.9%. So if we doubled that amount approximately and treated 31,700, about 32,000 hectares, that 0.9% results in an 11% reduction in the likelihood of burning. What if we made them even bigger, 500 meters? Well, that really stops many fires. It's hard for most fires to jump 500 meters. 50,000 hectares, that would be 50,000 hectares of high hazard fuels, 1.4% of the landscape. So now we're getting larger numbers, but it's still a small percentage, a 19% reduction in the likelihood of burning. The other scenarios are treating all the fuels. So this is kind of a scenario where we take those pod buffers, those buffered pod lines, 100, 300, 500, treat all the fuels in them regardless of hazard. So all the high hazard, medium hazard, even low hazard, treat that. The amount of area treated to treat all the fuel in the 100-meter buffers is 94,000 hectares. So a lot of area, and you get a reduction in likelihood of burning of 9%. If you go right up to the 500, that's 10% of the landscape. If you treated all the fuel in 500-meter buffers, that's about 10% of the landscape. Huge amount of area, 353,000 hectares. You get a really big reduction in hazard, in likelihood of burning and hazard. Now, what about the other scenarios that just treat high hazard fuel? Well, I don't know about you, but I don't want to look at tables of numbers like this too much. So let's try to graph them and let's plot them. Now we'll see if this works. I know it's a bit much, but really, if you look at this graph, each dot represents one scenario with 10,000 fires. The x-axis is the percentage of the area treated. We would expect that as you treat more of the area of the study area with fuel on it, you expect the amount of the reduction in likelihood of burning to increase. So that's what the y-axis is the reduction in the likelihood of burning, reduction in burn probability. So by definition, almost, as you treat more area, you expect your effectiveness to go up. The red line is the one-to-one line. That's basically the minimum. If you treat 10% of the landscape, you would expect at least 10% to be reduction because you've treated that 10%, those stands kind of treated. The area above, if they go above that line, that's the landscape scale effect. That's the effect on those treated areas stopping fires and reducing fires from spreading and becoming larger than they would have otherwise. The three light blue lines are the high hazard pod scenarios. So those are, when you're getting into 0 to 2% on the left, that's where most scenarios are because that's more in the feasibility range. And you can see as you treat more high hazard fuel in the pods lines, as you widen the pods and treat a bit more fuel, the effectiveness goes up. You get an increase in your benefit. And all of those are above the yellow dots. The yellow dots are the corresponding scenario treating any high hazard fuel elsewhere in the landscape. So what this is showing, because the light blue lines are above the orange lines, what it's saying is, if you've got a relatively small budget, that treating the fuel in pods, it gives you more of a benefit, more of a reduction in likelihood of burning than treating high hazard fuel anywhere in the landscape. That scenario changes when you start looking at the dark blue dots. Those are treating all the fuels in the pod lines. And in that case, if you've got larger budgets, then it's actually better to treat high hazard fuels outside pods than to treat lower hazard fuel in the pods. Treating all the fuel in the pods is a huge cost, and you're getting diminishing returns. Like why, you don't get much benefit from treating medium and low hazard fuels in the pod lines as much as if you treated high hazard fuel elsewhere. So this is the effectiveness. Now, because the effectiveness goes up as you increase the area treated, I want to normalize that and get at what we call landscape scale treatment efficiency. So this is the effectiveness, the reduction in likelihood of burning compared to the area treated, the percentage of area treated. In other words, for every percent of area treated, what benefit do you get in terms of reducing likelihood of burning? And this now normalizes it so you can actually compare how efficient is this? We expect there to be diminishing returns. As you treat more and more area in the landscape, we expect likelihood of burning to go down, but we also expect the incremental benefit to be less and less. So what we see, again, these light blue dots focusing on pods and high hazard, they are increasing and they're starting to cap out. We don't know. We need to run more scenarios to see if we can get more efficiency. But basically what it's saying is, as you treat wider areas of the pod lines, consolidate your treatment in structured ways in the pod lines, you are getting an increased efficiency, meaning you're getting a higher landscape benefit, not just the stands treated, but the benefit outside the stands treated compared to the high hazard. The the pod all scenarios, that's treating all the fuels in the pod, are all low efficiency. Why? Because you're treating areas that have low hazard in the first place. You're treating areas up in the mountains around the, the tree line. It's not a very efficient process. The orange dots are very interesting to me because what it's showing, these are the scenarios that just focus on treating high hazard fuels, the highest hazard fuels anywhere in the landscape, with a certain treatment level of either 0.4%, 13,000 hectares, or 30,000 hectares, right up to 353,000 hectares. And the efficiency goes up at first. As you treat more high hazard fuels, you get a increasing benefit. And then it starts going down. There starts to be a decreasing benefit, decreasing return on that investment of treatment. So this is just another way to look at it. And it's difficult to really wrap your mind around all of this. What we're going to be doing is filling in more scenarios to try to map out what the patterns look like to help guide inform strategies on which types of treatments strategies might work better at landscape scale. And with that, I'll pass it back to Don.
Yeah, so just a couple more slides here. And I want to talk about as you can see, we're kind of doing all these runs and how we compare between them. You can see some of these graphs that we're starting to come up with. But we want to kind of focus in on getting at some specific indicators for reporting out on how to kind of frame these scenarios. So as we've seen, the treatment effectiveness and efficiency kind of set of indicators that we're starting to work up, and some other ones that are kind of related to wildfire resilience objectives around fire size, fire pattern, and fire severity. We can look at shifts in amount of fire in different fire size categories, and that's what this graph below is showing, is the fire in each one in a different fire size categories, and then comparing between scenarios to see how that graph changes in terms of the numbers in each one of those columns in those categories. And then fire severity, we're partnering up with Canadian Forest Service, Cerise Barros, on doing some severity modeling and trying to figure out what we have the intensity part of the equation, which is the exposure, but then how does that interact with the underlying kind of stand characteristics to get at, what it might mean in terms of the severity of the fire in that place to get at that statistic. So we're still exploring this piece. So it's great that we're partnered up with Canadian Forest Service for this because they've been doing a deep dive on it. Fire frequency, we expect to see if you've got more area treated and, fires aren't going to start in these treated areas. So naturally with the more treatment area, you're going to have less frequent fires. And then again, kind of looking at the fire hazard with how it correlates to other values. So for example, we can overlay the fire hazard with ungulate winter range, high biodiversity areas, other values in the landscape to see what portion of those are high hazard, particularly in a treatment area. What are we looking at in terms of where other values are within that high hazard within those units to kind of inform some thinking around how we might want to manage those other values. And similar fire pathways, I think everyone kind of comes to this one pretty easily, that, where the fire is going to come into town from and what can we do between us and where the fire starts to try to mitigate that. So the fire pathway to inform some of that. So kind of working up some ways of kind of communicating that and comparing across these reports. So just to give you a kind of overview of where we're going next, you've kind of heard some of the challenges that we've been dealing with. So one of the pieces around this breaking, as opposed to just all fuel in a pod or just the high hazard, to start to look at, well, what happens if we do high hazard plus the medium hazard? And again, looking at, you saw these pod lines, do we maybe start to stratify the landscape and where there's more active kind of treatment happening, say in the WUI areas and around important values, and other areas like in the backcountry where you're maybe not doing those treatments? How can we stratify those treatments across the landscape to get more bang for your buck around things that are really important to people? And similarly with a value focus, so it's a similar kind of situation there. And then this 100% effective assumption that we've made, maybe in the first year, and realistically it's maybe 90% effective. Second year, maybe it's 70%. By the time you get to third year, maybe it's 50%. I'm just pulling those numbers. Gene probably knows better than me. But trying to get at that question. So maybe we're looking at, when we do, say, lay out 12,000 hectares of treatment, stratifying that way in terms of what effectiveness we would expect to find in each of that kind of annual treatments as it progresses through time. And that's kind of where we'll be working on this kind of over the summer into the early fall. And then longer term, we've been doing some thinking about how does climate change interact with the fire modeling in terms of more intense fire weather, wind affecting rate of spread, and some of these other components that we're thinking that climate change will interact with the wildfire. And then as well, we're building up some conservation pieces around looking at, again, it's this kind of value focused around aquatic ecosystems, biodiversity, where there's conservation connectivity, and to kind of look at that, how that interacts with kind of these different treatment approaches in order to come up. And these things are always like trying to fit together all these puzzle pieces to come up with something that addresses the values that people want to see maintained in the landscape. And then we're just ramping up into a carbon component of this project as well around, and there'll be more of that coming in probably fall. We'll probably maybe start to kind of talk about that a bit more as we work plan that up. But that kind of funding is just kind of landed, so we're just now just doing some initial work planning around looking at carbon within using this model to track, release of carbon and carbon storage and that kind of carbon accounting component.
Even though those graphs only have a few dots on them, that's been I think fairly thought-provoking for us, and I think they really help set the stage to do these short-term scenarios, to really look at other other things that might be done, and we want to fill out more of the map out more of that space on those graphs, look at these other options, and then be able to really provide information that in a way ideally that could be useful for thinking about planning on the landscape.
Great, thank you. Yeah, we do. There's kind of other work kind of intersects with this around benefits you see from, say, 40-year-old plantations, not burning as much as younger or older forest. See benefits in some places under certain weather around deciduous. So you sort of see these puzzle pieces. Piece we're focused on here really is trying to inform around how much treatment, where to do the treatment, and what you should be treating in those areas, and then and perhaps part of that, and I think that kind of, again, we had this December workshop, having another one in November, kind of having these types of conversations where we kind of like bring in some of these other elements to kind of start to bring into the modeling. But right now we're kind of looking at, say, for deciduous, we sort of see that deciduous maybe burns less when it's low fire weather, but high fire weather, we see deciduous burning just as much as everything else. So just trying to really want to inform, if we can slow fire down with some of these treatment strategies, then it gives time for suppression. It gives time for perhaps deciduous being more effective as a break.
And maybe I could add to that one of the advice, if someone put me on the spot and said, what advice would you give to a land manager right now? Well, given that the treatment budgets are likely limited, we can't treat 100,000 hectares, and given that it takes time to implement them, I would say the focus it says you need to be really strategic of where you place those treatments. Focus them in a structured way, have a good design of your pods, identify the highest hazard areas in those as well as nearby to have the biggest benefit in a structured way, because that's the thing. It's not just treating high hazard stands, it's treating them in a structured way that disrupts the fire and gets the benefit beyond just the stands treated, and doing that in a way that's focused not just in the amounts but spatially to near the values you care about, whether that's communities or other ecological values or cultural values, to get the benefit closer to those values rather than way out in the hinterland where we maybe aren't as worried about fires spreading naturally.
And you see in some of our upcoming work, we really want to kind of drill into that a little bit in terms of these priority areas and priority values, and start to say, okay, how much benefit can you get for these high value places? And processes like the forest landscape planning and the Bulkley-Morice kind of helps with some of that as well, just in terms of putting some thinking through about what can be done. But Jim's asking, do the scenarios include anything around different rates of cut and mill closures? So what we kind of stay at a strategic kind of level, like in terms of what does a treatment look like? We just assume a treatment's happened. We don't know what it's looked like. We don't know what the rate of cut has been in there. We just look at that. There's an outcome that says this much area has been treated and it's this effective.
Forest practices are harvesting is happening by current standards, by current law, and also at the current cut level, and that the current cut level is being achieved. But I think, I mean, it's an easy scenario to look at. What happens if you don't have that tool of forest harvesting? What could the future look like if that declines? That could easily be another scenario that's run, but not in these scenarios.
As Dave's unmuting here, Dave's one of the part of the team on the project and has done quite a bit of work on trying to understand the fuel typing and relate it to our landscape.
And we should thank Dave, and I meant to acknowledge Dave's work in the adjustments to the fuel types in the mountain pine beetle and recent fire areas. So before he speaks, we can acknowledge him.
Yeah. Thanks so much. I'll follow by saying that was a great presentation. What I'm curious about is kind of whether you conclude that the hazard across the landscape was related to it just being more dispersed versus being sort of concentrated on a pod line, or whether the pod lines were actually located in good locations to disrupt fire.
So I can address that a little bit. To get the full answer is going to involve some calculation, and that's a later thing. I think it's a really good question to look at. But what I can say is when you treat all the high hazard fuels in the pod line, say it's treat all the fuels in the pod lines above 50%. When you take that same area, let's take the 13,000 hectares. When we treat that same area outside anywhere, not within or outside highest hazard, the average hazard is higher. You're actually able to treat more fuel that's 70, 80, 90% hazardous. So you have a higher, so when you target you have the same area to treat and you target it into pod lines, by necessity or almost by definition, you're getting lower hazard stands being treated. They're still high hazard. They're just at the lower end of the high hazard as opposed to the really high hazard, 70, 80, the extreme. So that is true. So now when you see the differences, if the pod scenario has a higher benefit, even though it's treating slightly lower treatments, that's because of the pattern.
There's an operational consideration as well, is that some of the pod boundaries are associated with roads, or quite a few of them are actually, meaning that you can get in there and operate, whereas if you were to go to some other parts of the landscape, it may be more operationally challenging or less feasible to get out there.
So right now we're taking our starting fuel type layers, the 2024 BC fuel type layer. That's our basis. Basically, when we run one of those scenarios, we're assuming instant. So that's another unrealistic. We're not playing it out over time. We're saying you got a 13,000 budget. You can do it tomorrow. So you snap your fingers, you lay out 13,000 hectares of treatment for that scenario, and it's done. Now, is that realistic? No, this is about math. We got to control something. You could ask what happens if you could only do that over time. What happens if you've only done half of that? Well, that's a different scenario. So we're not really looking at that yet, but could we? Yes, absolutely. You could look at that. And as Don pointed out, you could also look at what happens if it takes you 10 years to say do that. What happens if the treatments you did in the first year are now growing back and now they're slash type, so they got small bushes, something else on it than no fuel. What's the what does that do? So there's lots of questions, and they're all narratives, I think, related to Jim's question. Each of these scenarios is a kind of story or narrative that we tell about what's happening, and the closer you get to something realistic, the more informative it is, but the more complicated it is. So I think we got to get there slowly as we roll out these simulations.
In the larger picture, that for example, Andrew is running the timber supply model for the Morice Bulkley. So, and that also runs in Sellies. And I mean, we've been doing this for years, kind of linking in whether it's a wildlife habitat supply model or a land use planning model, kind of developing all these modules, cumulative effects module, onto this platform that we can at the same time look at questions around timber supply and looking at, you know, the management regime, the current management regime or alternative management regimes, and run that over longer periods of time. Of course, as soon as you start to run over longer periods of time, you have to generalize more. So really looking at this 1 year kind of helps us understand it. And as soon as we start to project over longer periods of time, we kind of just take that understanding and generalize it to a certain extent in order to look over longer periods of time. We are designed, the system is designed in such a way to enable that activity.
I think I get where you're going. I mean, two parts to that. One is, are we running on average conditions? Well, we calibrate and validate against large fires. So we originally started with, you know, fires over 10,000 hectares, but we're looking at fires at least over 100. So we're at the landscape, we're not worried about 100, you know, small fires. And then when you look at the start years, the likelihood of when in the year, in the time season at those start, they tend to be in the higher hazard. So we're not really just going for average conditions. We are going for conditions where those fires burn. But could you assess extreme conditions? Well, that relates to what we're thinking about with climate change. We don't want to get into modeling weather in the future and the wind in year 2050 or something. That's way off out of our wheelhouse. But you could look at historical weather and identify when were those extreme conditions and postulate that you're maybe more likely to, you know, one scenario might be an increase in those extreme conditions. And there's a scenario, what if you had more extreme conditions? So hence likely higher, you know, higher values for the fire weather, or maybe windier, but maybe higher buildup index, things like this. That maybe, you know, what does that translate to these metrics? So that's something that's on our to-do list. So we've done these simple scenarios. We are working with this, you know, or even in communication with Steve Taylor at this Canadian Forest Service. They're looking at pod work elsewhere. And we've also, our group's been talking with people in California and other places doing other pod work. So, you know, comparing what they're expecting, the effectiveness is definitely something that we're doing in the background. But one of the challenges, of course, about effectiveness is it's actually really hard to test, because how, you know, you only got one landscape. So how do you really, and, you know, having experimental fires on the landscape is difficult. So to know really what that effectiveness is a challenge. So it's going to take work to kind of work through what is a, you know, as opposed to these 100% treatment, what is a likely effectiveness of these pods given what we know about landscapes and actual treatments on the ground.
And as we mentioned, we have this knowledge report, because one of the challenges we have is how fire and treatments work in our part of the world is different than how it is in the southern part of the province or in California. Is trying to localize that science and understanding as much as we can for this landscape. And Larry McCullough did a presentation last spring on kind of the treatment piece and kind of bringing that to this landscape. And again, in the knowledge report in the coming weeks, there's a chapter in there that kind of digs into this a bit more.
I see there's a question online from Angeline, and so about what would you need to incorporate in order to track carbon storage release? Well, the TEF model itself, as you might, if you guess, doesn't do carbon. The most likely tool to assess carbon storage and emissions would be the CBM, the Canadian Forest Service CBM model. There's other tools as well that could be explored, and we're talking about that with some other groups. But one of the ways you do that is you'd probably wouldn't use TEF directly. You'd use TEF to output some information that could run through a forest landscape model, such as what I'm using to support the forest landscape planning process and the timber supply review process. So there you could actually get at volumes and a growing stock on the landscape and volumes harvested and applying disturbance patterns at that level to get an estimate of what is the likely release with the fire regime that we're seeing and the harvesting regime, and what is the forest carbon stock on the landscape. So that could be done, and that's what would be needed, is you'd need to go through and bring in all the information that then could be used for one of these carbon models. Then aside, actually, I'll finish up with or add to that. it's not something that we're speculating on. I've for more than 15 years been providing analytical support for the carbon projects in the Great Bear Rainforest and Haida Gwaii, which are probably the largest forest carbon projects in Canada. And so, I've been linking up these forest landscape models with the CFS, the CBM carbon budget model for many years. So it's something we know how to do, and we're going to evolve that.
Thanks very much, everybody. It was great.